Have you noticed that robots are suddenly everywhere, and they're doing things we used to think were impossible? For decades, robots were stuck on rigid, invisible tracks. They could only do exactly what they were programmed to do, over and over. But today they're breaking off those tracks and navigating the real, unpredictable world. So, why are robots suddenly getting so smart? Let's break it down. The biggest challenge for a robot is what we call the messy room problem. The real world isn't a neat, organized factory floor. It's chaotic. Imagine accidentally knocking over a cup of coffee on your desk. To you, it's just a mess to clean up. To a traditional robot, it is a nightmare of physics. It has to calculate. What's the friction of a table? How heavy is the cup? What shape is the spill? The real world is simply too complex to hard code every single variable. To solve this, scientists had to completely change how they programmed robots. We moved from giving them rules to giving them experience. Old robotics was like reading a massive blueprint. It took 1,000 lines of code just to tell a robot how to pick up a single block. New robotics is more like going to the gym and lifting weights. Instead of writing endless code, we just give the robot's brain 10 good examples of how to do a task, and it learns the pattern. We call this imitation learning, or the copycat protocol. Think about how you learn a new trick on a skateboard or how to play a chord on guitar. You watch someone else do it, and you copy them. Robots are doing the exact same thing now. A human can physically guide a robot arm through a task, or let it watch a video. The robot records the data, copies the movement, and suddenly, it knows how to do it. And the crazy part is how fast they learn. Thanks to something called few-shot learning, a robot doesn't need to look at 1,000,000 cups to understand what a cup is. You show it a wine glass, a ceramic mug, and a paper cup. From just those few examples, its brain instantly connects the dots. It becomes a quick study, immediately recognizing any object that holds liquid. This is all powered by a totally new kind of digital brain called a V.L.A. That stands for vision, language, and action. Here is how it works. It uses a camera to see its environment. It uses language models, just like the AI chatbots you use on your phone, to understand the commands you give it. Then, it translates that vision and language directly into a physical action. It doesn't just run code anymore. It actually understands what you want. But how does it know the exact physical path its arm needs to take? It uses diffusion. You've probably seen AI image generators that start with chaotic TV static and slowly sculpt it into a beautiful, refined picture, right? Robots use the exact same technology. But instead of sculpting a picture, they start with a chaotic mess of possible movements and mathematically sculpt them down into one perfect, refined physical action. Now, teaching a robot all of this in the real world is a massive headache. We call this the hardware bottleneck. Physical robots run out of battery. Their joints break. And training them in real time is painfully slow. If you want to teach a robot to fold laundry perfectly, doing it in the real world could take months of trial and error. So what's the solution? We put them in the matrix. Literally, engineers build accelerated, three-dimensional virtual simulations. Inside this digital world, time moves 1,000 times faster. The robot's brain can practice a task millions of times overnight. Once the brain has mastered the virtual world, engineers download that brain into the physical robot. This pipeline is called sim to real. But sim to real isn't perfect. There is a catch, and it's called the reality gap. Inside the simulation, the math is perfect. Gravity is constant. Objects don't randomly slip. But out here, physics is messy. Lighting changes. Motors lag. If the gap between the perfect virtual world and the messy real world is too wide, the robot gets confused and fails the moment you turn it on. To fix this, engineers build a bridge using two things: physics tuning and visual realism. They intentionally add random noise and imperfections into the simulation to make the virtual physics just as messy as the real world. They also upgrade the graphics, so the simulation looks identical to reality. By making the Matrix as chaotic as the real world, the robot crosses the bridge without even noticing. Once it is successfully operating in the real world, the robot uses something called embodied thinking. It's no longer just processing data, it is thinking through its physical body. It looks at a scene, breaks it down into a step-by-step checklist, like Step 1, move left. Step 2, open gripper. Step 3, grasp, and smoothly executes the plan. And here's the absolute coolest part, the flywheel. Every time the robot acts, it observes the result through its camera. It thinks about what happened, it practices, it acts again, and the cycle continues. Every single mistake is captured as data. This means the robot is constantly getting smarter every single day, all on its own. Because of all this tech coming together, we are at a massive turning point in history. We are finally taking these incredible machines out of perfectly controlled laboratory environments and getting them ready for the ultimate frontier, our everyday living rooms. The era of physical AI is here, and it is learning fast. So, I have to ask, if you could drop a smart robot into your house right now, what is the very first task you would give it? Let me know down in the comments. Make sure to hit that like button and subscribe for more deep dives into the future of tech. See you in the next one.